I'm excited to introduce the Magic Wand application. First, I'm going to talk about the goal of this application, and then I'm going to talk about how we can actually utilize the IMU data along with the TinyML system we have in order to realize the application. Now, here's a very simple magic wand. And now with this wand, it's got a simple LED at the end of it. And the ultimate goal of this is to recognize some kind of gesture that I'm making with this wand. So let me start off by asking you if you can recognize this gesture that I'm actually doing over here. And well, if you guess that the number is 0, then you're right. Now let's say I'm writing another number over here. And what is this number? Can you guess what it is, right? And if you guess that the number is 8, excellent. Now the question is, how do you know just by looking at my simple gesture that the number is actually a 0 or an 8? And that's exactly what you're going to try and figure out and realize that, using the TinyML system with the inertial measurement unit that we talked about earlier. Now, before we get into something, complicated about looking at motions in 3D space like that, let's take a step back and let's just say that, we have this very simple magic wand. And the goal of this wand is also quite straightforward. Whenever I swing it in a particular direction, I want the LED off. And when I swing it back in that exact direction, I want the LED to turn on. And now stop for a moment and think about, how you might be able to do this with an IMU. Now, an IMU has got an accelerometer inside of it. In other words, the IMU can actually tell when there's a sudden change in a certain direction. And I could very well use that to be able to say if the wand was swung in a certain direction or in the opposite direction. And if it turns out that I swung the wand in a certain direction with a certain level of acceleration, and if that acceleration exceeds a certain threshold, then I would be able to say, turn the LED on. And if I wanted to turn it off, I would simply look for the exact same level of acceleration and then realize that, well, now I need to turn the LED off. And this works really great for simple gestures like just waving it in, with a certain speed. Well, what if I wanted to do something more sophisticated and complicated, like, the example that I'm showing you here, where I want to draw a gesture like the number 0 or the alphabet letter Z like this. And how do we go about doing that? Well, let's see, what we could happen if we just fall back to our non-machine learning methods and just use a simple accelerometer-based methods. Well, we could try and threshold things on a sequence. We could try and build a sequence of the certain actions that we are making and be able to see if those sequences match, the predetermined categories as we registered them earlier. So for example, if I want to draw the number 0, how am I going to go about doing that, right? Well, I might move the wand to the right. And so that's why I register an acceleration, on the x-axis has increased quite a bit. And I record that. And then naturally, I would want to move the wand down, which means that, the y-axis acceleration increases, and I want to record that. And then I would want to move the axis again to the x for the bottom curve, and I want to record that and finally record the y. So I can actually take this sequence and try and match it to some sort of historic recorded sequence and see, well, does it line up with the previous recorded sequence? And I know that it then corresponds to this number 0. Well, conceptually, that would work. But there are a lot of nuances in, actually getting this to work robustly. And this is challenging because it ends up being very sensitive to the speed and the shape of the gesture. Even small differences could lead to major issues. In other words, even though, you're writing the number 0, well, small variations in the way that you've done it could lead to mismatches, and that would become problematic. You won't have a very robust solution. So can we do better? And the answer is absolutely yes. One idea is that you can use the angular position, which gives you much higher fidelity in terms of the recording you're making. An improvement of this sort of using angular values that we get from the gyroscope is to be able to map the position of the IMU onto a spherical coordinate system. And this also helps in mitigating the problem with differences in the gesture speed, because we are actually getting the shape and we don't have to worry about the temporal aspect as much. And we also get the, we don't have to worry about the speed, and we also, the directions that we are estimating are are getting integrated over time with that, right? So we actually get the overall shape that we are making. Well, that's one step forward. However, there's a gotcha with that too. And the gotcha is that it's kind of hard to visualize, in this kind of spherical coordinate system. And therefore, it's hard to classify, what this number or alphabet might be. Well, what can we do? In order to visualize it, then we could turn that, angular rotation in 3D that we have in the gyroscope into a two-dimensional plot of the gesture. And this allows us to more easily visualize the data. Now we can take those points that we have collected and then turn them into a 2D image through a process called rasterization. The images are, have a defined size, and that's more standard and easier to compare to each other. And so that makes it easy and for us to effectively then save these references to disk. And in future, then when we do a certain sequence, we can actually do the rasterization again and just compare them image to image. And specifically, we can see that, what's the root mean square between the two of them. And if it turns out that this root mean square error between the gesture and the reference is small, then we can classify them and say there's an actual match. And that seems great. Well, let's try and understand what the full pipeline would look like now. The full pipeline would start with the vectorization of the IMU data that's coming from the input side, which we would then rasterize and flatten into a 2D image. And then we would save that as a reference. And then with future inputs, we would then rasterize them and then compare them to that reference that we actually have in order to classify this gesture as an output. Well, that seems great and is certainly a step forward. But let's see what ends up happening. The problem with this method is that it directly compares a single saved reference, meaning our classification is very sensitive to changes in shape. And now, therefore, we are sort of back to the square one problem, where subtle changes, don't really help us, address these fundamental issues. And now, one place where learning is very useful, that is useful in dealing with these small variations as noise. And it learns to ignore these small variations and just tries to figure out the general structure that's actually being encoded in the image. And so one approach is to just take the raw sensor data that we have coming in from the IMU, and we feed that straight into the neural network and ask it to predict the gesture. What if we just do that kind of end-to-end approach, right? That would be this end-to-end learning method. And now this would require a lot of data and would require fairly large, model in order to get good accuracy, especially in complicated gestures, right? So this is not really a preferred method if you want to do some things in a tiny ML system. However, if we go back to the original proposal that we had, which, was certainly an improvement, when we are able to take this, image input, and then we are able to flatten and rasterize it. And then the problem that we previously had was our comparison method was just flawed. And we need basically a more robust comparison method. Now, what if we, instead of, we just use a neural network in place of the root mean square error check, just in that location only, not covering the entire application? We already know that neural networks are awesome at being robust to small variations in input. So therefore, we could use the neural network to actually do the comparison. Now, this is awesome because it means that suddenly we are able to take this existing pipeline of being able to take the input, do the flattening, use the machine learning method for what it's really good at in doing the classifications. In this way, we'll be able to realize a rather robust magic wand application that's capable of recognizing gestures, specifically gestures that correspond to alphabets and numbers. Hopefully, the key takeaway that you are getting over here are twofold. One is, the IMU's data is actually really rich. So you can actually do very cool applications like learning, recognizing certain gestures. And two, you don't necessarily want to use machine learning end to end because it's not necessarily the best approach. So you want to understand, when to use traditional methods and when to incorporate machine learning, and how to couple essentially these traditional methods with machine learning at the right place where it's most effective. In our case, where it's effective is robustly classifying images which are coming in from the rasterization process, which is totally non-machine learning based, right? The inputs. So keep that in mind. So in the next lesson, I want to walk you through how you actually go about implementing that from a code perspective.